In this second video or third video for Chapter 2, we're going to look at a third type of first-order differential equation, a third technique and type, when a differential equation is not separable or is not linear. We may be able to solve it if it is an exact differential equation. And to determine if a differential equation is exact, we need to write it from its typical dy dx equals form into this form. So we separate off the dx and the dy and find the functions m and n that multiply respectively the dx and the dy. A differential equation will be exact if it satisfies this property. So this property right here, that the partial of the function m with respect to y equals the partial of the function n with respect to x, is what's called the test for exactness. So if we take a differential equation that is in this m of xy dx plus n of xy dy form, let's take a look and see if it is exact. So I'm going to, at this step, assume that you know how to take partial derivatives, and then on the next Blackboard we'll look at several examples to clarify how to do that, because a lot of you haven't learned how to do that yet. So the partial of this m function with respect to y is equal to 2x times 2y plus 0, and the partial of this n function with respect to x is y times 4x, and so therefore, or because those two are equal, we do have an exact differential equation. So before we go back and find out how to solve a differential equation if it satisfies the test for exactness, let's see how to take partial derivatives. So let's start with this function f of xy equals x squared plus y squared plus 15, where we have the variables x and y separated and the constant term separated. And let's say we want to take partial f, partial y. So we're going to, when we take a partial derivative, without going into the formalities of how they are obtained, the way to do it is just to treat all variables that are not y as if they were a constant. So when we take the partial of this first term, we think of the x squared as being a constant, and we think of, and we already know that the 15 is a constant, so the derivative with respect to y of those two terms is 0, and then when we look at the y squared term, we just differentiate it as we normally would. A derivative with respect to y and a partial with respect to y in this case are the same thing. Then what happens if we want to take the partial of f with respect to x? Then everything that is not the variable x is treated as if it's a constant. So the y squared is a constant, and of course the 15 was we already knew that was a constant. So when we take the partial with respect to x, this first term, in differentiating this first term, we just take its derivative as we normally would. We get 2x, and then we get plus 0, plus 0. So now let's see what happens when we have a function of x and y where the variables x and y are bound up in the same term. So let's suppose we have this function 2 here, and we want to take its partial f, partial x first. So we're going to do the same thing. We're going to treat everything that is not the variable we're taking the partial with respect to like it's a constant. So this y squared is treated like it's a constant. This whole term is treated like it's a constant. And so let's make note of the fact that from Calculus 1, if we had a constant times a function and we took its derivative, that constant remained, and then we took the derivative of just the part that was with respect to x. So we're going to do the same thing here. When we take partial x of that first term, the constant remains, and then we take the partial of the part that's with respect to x and get 2x. When we take the partial of this second term, it is 0 because everything is in another variable besides x. And then when we take the partial of this last term, everything is in the variable x, and so it's just a derivative as normal. So now let's go to the next blackboard to see how to take this function's partial with respect to y. So we do the same thing in identifying what is constant with respect to the variable y. So this factor x squared is treated like it's a constant, and this whole term is treated like it's a constant. So we repeat the constant and take the derivative of the y squared and get 2y. The derivative of this term is just a normal derivative because it's all in the variable y, so that would be what, 4y, and then the derivative of this term, because it's all in the variable x, is just 0. So if we go back to where we were in determining the exactness for that differential equation and go through it again, when we take the partial of this term right here with respect to y, we treat the 2x as a constant, and we just take the partial of the 2y with respect to y, or the y squared with respect to y, to get 2y. And then the partial of the x, or the 1, is just 0. When we go to take the partial of this second term with respect to x, we treat the y like it's a constant, so we repeat the constant and take the partial of the 2x squared and get 4x, and we see that 2x times 2y is the same as y times 4x. So as before, as we knew, it is exact. So how do we solve a differential equation if it is exact? Let's see that there's a 3-step process for doing that. So what are the steps to finding the solution f of xy of an exact differential equation? Typically we find the solution to an exact differential equation in the implicit form f of xy. So step 1 is to take the first step in finding this f of xy that we're trying to find, and we do that by integrating the m with respect to x, or we could integrate the n with respect to y. So in this case we're going to choose this way of doing it, and so let's set that up. So we're setting f of xy equal to the integral of the m with respect to dx. And here's the m, 2x y squared plus 1. So when we integrate with respect to one of more than one variable, we treat everything that is not in that variable as if it is a constant. So that means the y squared factor of this term is treated like it's a constant, and we're just taking the antiderivative of the 2x. So we repeat the constant, and the antiderivative of 2x is x squared, and then the antiderivative of the 1 is plus x. Normally we would put a plus c here, but because we're integrating with respect to x, it turns out we could have a function with respect to y as appearing here, and so let's call that g of y. Notice that if we were to differentiate this back with respect to x, the derivative of this g of y would be 0, just like if we had put a constant there, the derivative of that constant would have been 0. So, so far we know that f of xy looks like this. So let's see how we find the g of y. So what we're going to do is take this f of xy with its unknown g of y, and we're going to take its partial derivative with respect to the other variable. So we integrated back here with respect to x. Now we're going to take the partial of this f that we have and take its partial with respect to y. So we're taking the partial of this f, which is right here, with respect to y, and we are setting that equal to the n of xy, which is 2x squared y. So what is the partial of this with respect to y? Well, we'll treat the other variable, the occurrence of the other variable, as if they are constant. So those boxed in are treated as constant, and we get, and so in the x squared y squared term, we repeat the constant and multiply by the partial of y squared with respect to y, which is 2y. The partial of the x squared is 0, and the partial of the g of y with respect to y is g prime of y, and we're setting that equal to 2x squared y. Well, we see that we get a cancellation of 2x squared y on both sides, and so we just get that g prime of y equals 0, or g of y equals a constant. Typically, g of y is going to be some function. So if we put that back in, we have found g of y as a constant, and we have our solution now to the differential equation. Let's write that on the next blackboard. So f of xy equaled x squared y squared plus x, which we got on the first step, and then we found that the g of y was c. The way we typically write the solution of one of these equations is to put the plus c on one side and box it in like that. Notice that this differential equation, could we have solved it for x? No, because the x appears to two different powers here in this equation, or in this solution. We could have solve it for y, so it doesn't have to be in the explicit or the implicit form. So let's now take a look at a couple other examples, a couple more examples of how to solve a differential equation that is exact, and we'll start on next blackboard. So let's take a look at this differential equation. Let's notice that if we put it in its dy dx form by rearranging, that in this form we wouldn't be able to separate the variables, and in this form we're not going to be able to get it to be linear. So let's take partial m partial y and see if that is equal to partial n partial x. So partial m partial y is what? The derivative of the 1 is 0, the derivative of the next term, the e to the x, is like a constant, and the partial of y is just 1. And then on the last term, the x, e to the x, is like a constant, and the partial of the y is just 1. And then when we go partial n partial x, we're doing the product rule on this term, and so we get what, since everything is in the variable x, so we get x times e to the x first times the derivative of the second, plus the derivative of the first times the second, plus the derivative of the 2, which is 0, and we see that Yes, it is exact. So this time, let's do it the other way. Notice that it's easier to integrate the n with respect to y than it is to integrate the m with respect to x. So let's do that. And if we're doing that with respect to y, we are treating all of that like it's a constant. And so we just get the antiderivative of 1, which is y, and of course the 2 is a constant. That gives us a 2y, and then we have to add in not plus c, but a g of x. So that's our step 1. Our step 2 would be to take this f of xy that we found in step 1 and take its so we're going to take the partial of what we just found this time with respect to x, set it equal to m. M was 1 plus e to the x times y plus x e to the x times y. And the partial of this f with respect to x, so we're treating the y variables like they're constant. And we get what? So on the first term we copy the y over, and then we take the partial of x, e to the x, which is a product rule, so it's x e to the x plus 1 times e to the x. The partial of the 2y is 0, and the partial of the g of x is g prime of x, and then we set that equal to the m of xy, 1 plus e, which is 1 plus e to the xy plus x e to the xy, and we see that all of this cancels out with this, and we're left with g prime of x is 1, or g of x is x plus c. And so we just replace the g of x here with x plus c. And so let's write that out. And remember that we put the c on the right-hand side and set everything equal to that c. I've written the original differential equation below this solution. There is a faster method to find solutions to exact differentials, but you have to work backwards, and it's not straightforward. Notice that if we take the partial of this solution with respect to x, we get the x term gives us a 1, the 2y term gives us a 0, and if we take the partial of this e to the, or x e to the xy term with respect to x and use the product rule, we get this term and this term. And if we take the partial of this solution with respect to y, we get the 2y clearly goes to the 2, the x goes to a 0, and when we take the partial of this term with respect to y, we just get the constant part of it, because the partial of y is 1, and we get that. So sometimes we can work backwards and see this. So if we go back to our first example, and we took the we're just trying to find a function whose partial, a solution whose partial with respect to x gives m, and whose partial with respect to y gives n. And clearly our solution here does do that. Could we have seen that? Well, maybe just by working backwards, right? Taking the antiderivative of this term right here with respect to x, we see that we actually get everything on the left-hand side, and then does that work for the antiderivative of this term with respect to y, which gives us everything but the x and the c. So not so easy to work backwards, and so this straightforward method that we use, this three-step process, is better. Let's do one final example. Here's an example in two new variables. The m is a function of t and y, and so is the n, and so the test for exactness is going to be, is partial m partial y equal to partial n partial t. So what is partial m partial y? That would be, maybe we should write it out. So we've got e to the t y minus t e to the t, and the partial of that with respect to y is just going to be e to the t, and then partial n partial t of n is just going to be, easy to see that that's just e to the t, and so yes, it is exact. So the f of x, y, isn't it easier to work with the n again? So f of x, y is going to be the integral of 1 plus e to the t with respect to the variable here, the dy, and so what does that give us? Everything that's not y is treated like it's constant, so the 1 goes to y. The e to the t is a constant, and it's multiplied by the antiderivative 1, which is y, and then it's plus g of x. And then we're going to take the partial of f with respect to the first variable t, and we get what, 0 plus e to the t, because the derivative of e to the t is itself times its constant, and this should have been g of t. So this is g prime of t, and then we're setting that equal to the first element, which is the m, which is this, multiplied out. So this time g prime of t, the g function is a little bit more complicated. It is minus t e to the t, and that requires an integration by parts. So let's set that up. So this problem is made more difficult because that final integral is harder to do than typical. So u is t, dv is e to the t, we need the du, which is dt, and we need the v, which is e to the t, and then the parts formula, uv minus the integral of v du is t e to the t minus the integral of e to the t. We had a minus sign out in front of all this, so we get what? Minus t e to the t minus minus e to the t, or plus e to the t plus c is our g of t. So here was our f of x, actually it should be f of ty, and we had this, and now we've got g of t, so our solution is y plus e to the ty plus the g of t, which is minus t e to the t plus e to the t, and we set that equal to c. Are we convinced it's a solution if we take the partial t of it? So are we convinced that this is a solution? Let's take the partial t of the terms in this, and that should be equal to the m. So the partial of the first term with respect to t is 0. The partial of the second term with respect to t is e to the ty. The partial of the next term with respect to t is the product rule. So minus t e to the t minus e to the t. Partial of the last term with respect to t is e to the t. And so this and the last two terms cancel out, and yes, we get this. And now let's take the partial of this with respect to y. And see what we get. We should get this. And so the partial of the y with respect to y is 1. The partial of the next term with respect to y is just the constant for e to the t, and then the partial of the last two terms with respect to y is just 0, and so we did get this. So there are 3 examples of the how to determine if a differential equation is exact and how to solve it when it is. This 3-step process: an integration, a derivative, and then a solving for that g of x, g of y, g of t. So that's going to conclude this video on section 2.4 in your book.